Good morning, everyone. I guess you can see my screen.
Yes, it's visible. Thank you.
Yes.
Okay, perfect. So, yes. Okay, during yesterday's session, EC presented the general methodology and the structure of MAED model, the economic and demographic data needed, and also the other driving parameter. But from today, we will start to present different economic sectors, how they are structured and modeled in MAED. And today's topic is industry, and it includes actually 4 sectors. It includes agriculture, construction, mining, and manufacturing. So this presentation is structured into 3 main parts. First of all, I'm going to be talking about the structure of different industrial sectors and the different end-use categories. And then I will go on to present the formulas of calculation of final and useful energy demand, as well as the other theoretical aspects and the main calculation steps. Okay, but before, it is important to have a good understanding on how different sectors and subsectors are defined in MAED. Here we can see on the left side the main energy consumer sectors in MAED. We have industry, transport, services, and household, and this is also the aggregated structure of the results that you will get. But we can also define other subsectors. We will see this. And as you can see on the right side, there is 4 main subsectors in industry. We have agriculture, construction, and mining, and manufacturing. And this structure corresponds to what we have defined in terms of GDP structure in MAED. If you remember, this structure was presented yesterday. As I said, today we will start by presenting formulas and data needed for agriculture, construction, and mining. And after, we will discuss manufacturing. The modeling methodology is the same for all these sectors, but usually we separate manufacturing from ACM because manufacturing is a bit more complex, because we have some additional breakdowns, some additional level of details. We will see the split up by temperature level, etc. So we will see this in the next slides. Okay, this is a scheme which illustrates how energy consumption of industry sector is structured. We already said that we don't have to do. We can define more subsectors, but we don't have to do this unless there is a real purpose and an interest behind. And also if we have data. If not, we can model agriculture as one sector, as well as construction, mining, and manufacturing. So generally, we have 3 end-use categories that we are modeling in MAED. You can see them. We have specific use of electricity. We have heat for thermal uses and motive power. So the first category is specific use of electricity, and here only electricity can be used to satisfy this need. And also for regarding motive power, we have motor fuels. Again, we don't have a competition between other energy forms to satisfy this need, our need in terms of motive power. So we have only motor fuels, and motor fuels, as you know, are fossil fuels, but they are used to power engines, to produce horsepower, actually. But for this third category, this heat for thermal use, this category can be satisfied by various categories of energy carriers with electricity, and they are substitutable. It means that there is a competition to satisfy this need. This need of heat for thermal use. We can have electricity, we can have heat from cogeneration, we can have district heat. Also, we can have this solar system or solar thermal. And this solar is not solar PV. Solar PV is used to generate electricity. These are solar collectors that are used to collect the sunlight, the heat or the radiation from the sunlight, and then convert it to heat liquids. So to produce heat in general. This is the idea. And also we can use fossil fuels to provide heat in industry, as well as traditional fuels and modern biomass. And the difference between traditional fuels and modern biomass is efficiency. Traditional fuels are used at lower efficiency, and modern biomass, it could be biofuel or something with higher efficiency. And we have two additional categories in this final energy. You can see them in the left side. We have feedstock and coke. This is for non-energy use, and this is only relevant for manufacturing. I will come to this in more details in the next slide. So this is the general scheme on how everything is structured regarding industry. Okay, so let's start by ECM. As I said, we will start by agriculture, construction, and mining. Let's see what is relevant for ECM. Here, just to recapitulate, we have three end uses, as I said. Some of them are substitutable, like are non-substitutable, like specific use of electricity and motor fuels in the first bullet. Okay, it means that there is no competition with other energy form to provide the same end-use service. It means that electricity will be only, or to provide this specific use of electricity, I will only need electricity. And to provide motive power, I will only use in industry, they will only use motor fuels. So for this, we model useful energy demand equal final energy demand. Right? So, but if there is a competition, like in the case of heat for thermal use, then we will introduce efficiency. And each technology and each fuel has its own efficiency. And also I will come back to this concept of efficiency and how we convert final to useful later in the presentation. Okay, the energy demand in ACM is driven by the level of economic activities evaluated in terms of sectoral GDP, as it was presented yesterday. This is the generic equation that we can find in almost all sectors, and energy intensity. And that's why generally we link this industry to the GDP structure, because the main driving parameter in industry is the value added or the sectoral GDP. We see here the general formula, for example, using this equation, if I want to calculate yes, please. Yes.
Please, sorry to interrupt you. Can you give an example of the motor fuels? Since they both belong to fossil fuels. So, what example?
Example, it could be diesel. For example, it could be gasoline. It could be also kerosene. So it is the fossil fuel, but it is used to power engines, right? So in industry,
thank you very much. But somehow it's a bit.
Okay, perfect. Okay. Yes, please don't hesitate to interrupt me if there is something which is not very clear. Okay, I was saying that, for example, if we want to calculate our final energy demand, for example, in 2040, we need to multiply the energy intensity in 2040, which is energy divided by monetary units, of course, by GDP. Times the GDP, the expected GDP of the subsectors in 2040. So the formula is quite simple. And we can do this for motor fuels and also for, as you can see, for specific use of electricity. As I said, here there is no competition. We model useful energy demand equal final energy demand. But for thermal energy uses, energy intensity is specified in terms of useful energy per unit of GDP. It's not final divided by sectoral GDP. Here, energy intensity is useful energy divided by value added. We will see this also in more details with an example later in this presentation. And since there is a competition between various forms of energy to satisfy this need in terms of thermal energy, we will need what we call a market penetration of each energy form. And these market penetrations are like market share, the share of each energy form in the thermal process potential market. So this is also important. So here we have two additional parameters, penetration and efficiency. Again, this is a generic formula, but this time for useful energy demand, as I said, it is quite similar to the previous one related to motor fuels and specific use of electricity. For example, here again, if we want to calculate our useful energy demand, let's say by 2035, again, we need to multiply the energy intensity in 2035 by the expected sectoral GDP. And if we calculate the useful energy demand using the formula presented in the previous slide, let's say for a target year, for example, in 2040, we will need to convert the useful energy demand to final energy demand. Here we see the formula in which we have these two factors, efficiency and market penetration, standing between final energy demand and useful energy demand. So it is important to understand this formula, this generic formula of conversion of useful to final energy, because it will be applied also in other sectors, like in manufacturing, also in household, in service sector. So it is very interesting to understand this formula. Let's assume that in a certain year, we need a process heat for our industry, and we need to satisfy 100% of our need. And then this useful energy can be satisfied, let's say, by 30% of one energy fuel and 70% by another energy fuel. These shares are market penetrations, right? Market penetration of each energy form. And the sum must be 100%, of course. If in your calculation you find that the sum is not 100%, so there is something wrong. And let's assume that this 30% comes from coal boiler, which use fossil fuels, and the 70% comes from another technology, which is electric boilers that use electricity. So the next parameter is efficiency. So we will apply the efficiency of the coal boiler and the efficiency also of the electric boiler. And then you can, with this formula, you can calculate the final energy using these two parameters, as I said. We will see again this slide. This slide is actually quite important. We will see the same slide when we will be talking about manufacturing, because the procedure is similar. Another important thing to point out here is that we assume in MAED that the efficiency of electricity is equal to 1. It means 100%. Even if we know that in reality is not maybe the case, it could be about 90 or 95%, or I mean, more or less. But here we use the efficiency, as I said, for electricity as 1. For example, we have the efficiency of electric industrial boiler it is something between 90 and 95%. So here the idea is to calibrate all the other efficiencies to calculate them in relative terms. I mean, according to the efficiency of electricity. Okay, so for example, here we have 90%. This is the actual efficiency, but the efficiency is made here in this empty cell is 1. Okay, it's 100%. I should also adjust the other efficiencies for other energy forms according to this efficiency of electricity. We will see this also in another example. Yes, okay. So let's move to manufacturing.
Soufiane?
Yes, please.
Sorry, I have to come back again. The efficiency you're talking about, in what sense? In relative to what sense are we looking at this efficiency? Over.
Okay, so you will need, if I understand correctly, you will need efficiency to calculate in your calculation, different calculation steps. You will need, at a certain level, you will need efficiency to go from final energy to useful energy. And for electricity, we assume that all the electricity will provide 100% of the because useful is equal final. It means that electricity, we assume that the efficiency is 100%. But as I said, in reality, it could be a little bit less, a little bit lower. It could be about 95%. But just we use this as like standard, as default value in MAED model. And as I said, to treat all the energy forms fairly, you can adjust according to the efficiency that you defined for electricity.
So in other words, you're looking at it from the angle of ability, looking at it from the angle of loss within the system, complete conversion, right?
Actually, is not the losses, because here we are just the electricity consumption, which is reported in the energy balance, is the final consumption. So the losses is not included, right? It's a final. So here we are not talking about the losses. We are talking more about the efficiency. Okay, so let's say, for example,
okay,
I don't know if you.
Could you just elaborate something about the efficiency definition? Because my understanding is that efficiency is a factor of loss.
Yes, that's right. No, I thought you are talking about these losses in transmission and distribution. So of course, out losses, but of course, here we assume that there is no losses for electrical processes. We assume that the efficiency is equal to 100%. But of course, let's take an electric boiler. The efficiency of the electric boiler is not 100%. It's 90% or 95%. So you can use it. You can use the actual efficiency and then adjust the other efficiencies according to this efficiency of electricity. Okay, so but that's right. This is about losses, but I was thinking about this losses in transmission and distribution. Okay, but we will do this. I have an example in this presentation with some numbers and some figures. We will see the calculation, and then I think it will be more clear. Okay,
right,
if there is no... Okay, right. Okay, this slide is very similar to what we have presented for ACM. Again, if there is no competition between energy fuels, we have useful energy demand equal final energy demand. And this is the case, again, for specific use of electricity and motor fuels, where there is no competition between energy carriers. But for thermal use, again, there is a certain market competition. We have different energy forms. We have electricity, fossil fuels, traditional biomass, modern biomass, solar systems, all of them can provide thermal energy in the industry. So here we have something new, is that there is another breakdown of heat into 3 types of thermal processes with respect to temperature level. We will distinguish between high temperature level of thermal needs, medium temperature, and low temperature. And we will learn more about this breakdown in the next slide. This is why manufacturing, as I said before, is a bit more complex because of these additional breakdowns that we will be talking about in the next slide. Okay, similarly to ACM, in manufacturing, when there is no competition, we have this simple formula to calculate directly the final energy. We said that final energy demand is equal useful energy demand. For motor fuels in manufacturing, we have energy intensity for motor fuels, which is the consumption per unit of value added or per unit of sectoral GDP for respective subsector if we define them. Because in manufacturing, we can define subsectors because generally for manufacturing, data is available. Data from energy balance and data from national economic accounts by subsectors is available. So that's why in general we have the possibility to model subsectors in manufacturing. Subsectors, it could be basic materials, it could be equipment and machinery, it could be non-durable goods, etc. So that's why the formula here, we can use the formula for each subsectors. But here, okay, let me just emphasize something, because for this specific use of electricity, we have before this calculation, we have an additional step. We need to split up the electricity in manufacturing between specific use of electricity and the amount of electricity that will contribute in providing thermal energy. So we will see, for example, let's say in my country, I know that in manufacturing sector, the electricity consumption, 80% or 85% will go to specific use of electricity, and the 15% remaining will go to provide thermal energy. So we need to do this first split up. We will see this in the template and also in the calculation and also during the face-to-face training. We will start by this split up and then we will move on by calculation step. Okay, things are getting more complex when modeling thermal uses in manufacturing. We have this additional split up, as I said, of thermal use by temperature level. And this split up is applied for each subsector. Okay, we have, as I said, we have the high temperature level, we have the medium, and we have the low temperature level. And the top of this cube, you can see subsectors. Okay, we are not obliged to define subsectors, but if you need to do so, if the purpose of your study suggests to do so, you can define subsectors. And then for each subsectors, model this different temperature level of thermal useful energy. Okay, the challenge here is that this type of data by temperature level is not usually available. It's hard to get this data because in industrial surveys, generally they didn't ask usually for this information. But sometimes in my country, during energy audits, which aims to assess energy performance in some industrial sectors, some big industrial companies can report this information to the power utility or to the Ministry of Energy. So yes, this But if this data is not available, then we can define some plausible assumption. Because as you can see here in this slide, for each temperature level, for each temperature range, we have a certain competition between various energy fuels to satisfy these thermal needs by temperature range. So of course, each fuel has its own market penetration. What you have to keep in mind is not all of these energy carriers are competing on each temperature level. Because if you have district heat, it will not compete in the high temperature level, as well as cogeneration. So each category of energy, each category of fuel will, for example, it will be dominating in a certain level of temperature needed. So that's the idea. Okay, this is the main formula to calculate the useful energy in manufacturing. Again, we will use this energy intensity, which is useful energy divided by the sectoral GDP, and then we will need the GDP of the sector of manufacturing or the GDP of the subsectors. And then we will need something new here. Then we will need to multiply this by the useful energy share by temperature level and by subsector. We will see also this with another example. And this is the formula to convert final energy demand to useful. It is similar to what we have seen so far. You have the same two parameters standing between final energy and useful energy. But now it's a bit more complex because we have to sum it for the 3 temperature level. We are calculating this for low, medium, and high temperature level. Again, this is a similar example just to better understand this formula. If we want to satisfy a thermal energy, let's say this is a steam for processes, we want to satisfy 100% in manufacturing, and we know that this 30% will come from a technology or a fuel, and 70% will come from another fuel that use different technologies. These 30 and 70 are our fuel penetration, and then we will need this efficiency to calculate this this contribution. Okay, at this level, we have to know also that in MAED model, it is also possible to model cogeneration as energy source to satisfy our thermal needs in manufacturing sector. What we need to know about cogeneration is the final energy input is fossil fuel, and it produces electricity and heat in parallel. These two outputs are considered as useful in MAED model. Okay, I will not go in more details about cogeneration at this point. This is something that we can also cover during the in-person training. And for some of you who are interested to model the process of cogeneration, we can then dig deeper on this topic. But if we model cogeneration in MAED, you will be interested to these two parameters that you can see, this heat electricity ratio and cogeneration efficiency. Of course, for cogeneration efficiency, we can use some standards. We need to check some typical values of efficiency. Here there is some values for cogeneration plants. The efficiency is between 65 and 85%. And also for this ratio, this heat electricity ratio of different cogeneration installation, we can see here also some typical values. Okay, the last important thing in manufacturing that we need to know is this modeling of energy forms for non-energy uses. If you remember, I highlighted this coke and feedstock because in manufacturing, we have to know that MAED model enables us to model separately these two categories, this feedstock and coke. For example, if your country is a big producer of steel, then we have the possibility to separately calculate the demand for coke to produce this steel. Okay, so coke is a carbon-rich material used to make steel. So it is used for non-energy use. It is used in manufacturing processes to provide steel, to produce steel. So if the country is not a big producer of steel, then we can model the consumption of coke within the fossil fuels. Okay, if it is negligible. Also, feedstock is a non-energy use category. For the production of, let's say, fertilizers, asphalt, lubricants, it consumes energy fuel, but for non-electric energy use. For example, lubricants are not used to power engines, but typically used to reduce, friction between parts. Okay, in the next two slides related to coke and feedstock, I will not go in much details. This is just to show you the formula in case you want to model the demand for coke in your model. You will need the share of steel produced in non-electric furnaces. So we will need this fraction. You will need also the specific consumption of pig iron, which means this ton of pig iron by ton of steel, and coke input per unit of pig iron output. And with this, you will be able to calculate the demand of coke. And yes, it is a function of a ratio of the production of steel and raw materials in petrochemicals with respect to GDP of the first sector. Because the first subsectors in manufacturing is basic materials. And in basic materials, it includes heavy industry, including steel production. So that's why we link generally the value added of the first subsectors in manufacturing, which is basic materials, to the production of steel. So to do this, you need to have some time series, some historical data, 3 or 4 years, to establish this correlation between the production of steel and the value added. Okay, similarly, this is the formula to link the consumption of feedstock to the value added. Again, here we will need again the value added of basic materials. And of course, this is something that you can calculate outside the model in Excel and then enter properly the data in your MAED model. So yes, here just to have an idea that this is something which is possible in MAED, something that we can do. But again, if this consumption of feedstock of coke is not very important in your country, then this is something that we can simplify and then calculate this under the final energy of fossil fuels. So I will go straight to the definition of the sectoral structure and uses. Okay, this is, and yeah, to model subsector, this is very important. And to model subsectors in MAED, we need to make sure that the economic data or the GDP data is available. And also, we will need also the data from the energy balance. So we will need to make sure that the energy consumption from energy balance is available, as well as the GDP data. Unfortunately, we don't have necessarily the same level of disaggregation and details in energy balance and in national economic accounts. For example, if we have the GDP breakdown for some subsectors in manufacturing, if we have the GDP for basic materials, for machinery and equipment, for textile, industry, food processing, etc. But in other hand, we don't have the energy consumption with the same level of disaggregation in the energy balance. Unfortunately, we cannot model subsectors. So we need to make sure that both data are available for the aggregation level we choose, because defining subsectors is really up to the user. Here, for example, from this table, you can see in manufacturing that we have this sugar industry. We have the GDP for sugar industry, and for other manufacturing industries, we have both data. We have the GDP data and also energy consumption in the energy balance on the right side. So here we have the possibility to model sugar industry separately as a subsector of in manufacturing. So as I said, subsectors are a user decision. We generally recommend to keep the model simple. Regarding the input data, we will need first to calculate the energy intensities for different energy use categories, as it was presented in the previous slides. For motive power and specific use of electricity, energy intensity corresponds to the final energy divided by the sectoral GDP. But for thermal uses, we calculate our energy intensity at the useful level. So we will need to divide useful energy by monetary unit, by sectoral GDP. Also, the market penetration of energy form in thermal uses are also calculated at the useful level. Okay, let's have an example. And here we will be focusing in this slide, we will be focusing on specific uses of electricity and motive power. In the first table, we have our data from energy balance. So we have our final energy consumption. As I said previously, the first split up is related to electricity. So we will need to distribute this 122. You can see in the first table, electricity is about 122 point something, 0.48 or 46. So we need to divide this 122 between electricity for specific uses and for thermal uses. You can see in this second table that we assume that only 95.99 will go to specific use of electricity, and the rest will go to the thermal uses to provide heat. So this is the first split up from energy balance. We took electricity consumed in manufacturing. The first split up of electricity is between specific use and thermal. The big part, of course, will go for specific use of electricity, because there is some other energy forms that are better competing in energy to provide thermal energy better than electricity. That's why a small amount of electricity generally will go to thermal uses. Okay, so here we are calculating our energy intensities. For example, for electricity, we will take this 95.99 kiloton oil equivalent. We will divide it by the GDP of manufacturing, and then we will get our energy intensity for this end use category, for this electricity specific uses. We will do the same for motive power, but for motive power we will sum up this fossil fuel, this motor fuels, different motor fuels, and we will divide them by the sectoral GDP again to get our energy intensity. This is the first step, and this is for specific use of electricity and motive power. Regarding thermal uses, we have some additional calculation step. After the first distribution of energy fuels consumption among end uses, we will need to divide the final energy for thermal uses by temperature levels. Because as explained before, industrial processes require different energy form according to the level of temperature needed. For example, for high temperature furnaces, we will need, for example, I don't know, crude oil or other petroleum products with high calorific value to provide this heat at the high temperature level. Electricity also can contribute to provide this thermal use, maybe medium voltage or something, because it consumes a lot of electricity. And yes, different energy forms will contribute at each temperature level. And this is an example to how we can do this split up. I will not comment everything. I think that the steps are more or less clear. First division is by end users, and then we will divide the final energy for thermal uses by temperature level. And here we have just grouped these energy fuels in order to have them aggregated according to MAED structure of fuel categories. So from this first table to the second table, we just group them. For example, fossil fuels, we grouped crude oil, LPG, kerosene, diesel, fuel oil, and natural gas to have this category of fossil fuels. In traditional fuels, we have only one category, which is fuel wood. Okay, at this level, we will introduce efficiencies to convert final to useful. Each fuel or each energy form has its own efficiency. And then we will calculate the average weighted efficiencies considering the fuel share in each fuel group type. For example, in the category of fossil fuels, we have crude oil and we have diesel. And the efficiency of crude oil is about 74%, and the one of diesel is 84%. So we have two efficiencies of two different two different fossil fuels. And to get the average weighted efficiency for fossil fuels needed by MAED model, we will need to apply this weighted average. I mean, this is a sum product formula in Excel. To have this, you can see this 0.7888. So this is 78%. As you can see, we used the different efficiencies of each fossil fuel, namely crude oil and diesel. We multiplied them by the energy to get the, and we divide also by the energy to get this weighted average efficiency. This is the data needed actually for this is an input data to MAED model. And we will use this average weighted efficiencies to calculate our useful energy for thermal uses by temperature range. And finally, the fuel penetration by temperature level, again, in the second table. You can see, for example, this how we calculate this this fuel penetration. For example, let's take fossil fuels. In the first table for high temperature furnaces, the value is about 170. So we will divide this 170 by the total on the right side. We will divide it by 195 And then to get this 87%, this 87.46% fossil fuels in the second table, in the first row, high temperature. So yes, this is I try to summarize the main calculation steps for industry. As I said, manufacturing is a bit more complex because of these additional steps of calculation, because we need to distinguish between subsectors if we model them, and also, and mainly, these different temperature ranges. So I will go directly. Sorry, let me just plug in my laptop because I'm running out of electricity. Yeah, okay. So we will go directly to see MAED user interface and see how we can populate this data, this input data that we calculated before, namely energy intensities and efficiencies and market penetrations. So here, as you can see, there is a menu here, industry, in the left side, in industry, and then it will give us this window, and then we will start to populate our input data. First of all, we need our energy intensities for the first end use category, which is motive power. So we need to populate this for different sector. We need this for agriculture, construction, mining, and manufacturing. And it is very important to save, because there is no saving will not be done automatically. So after each modification, we need to save. And we need also energy intensities for electricity specific uses, again for different sector or subsectors if we define them. Energy intensities again for thermal uses. As I said, this is calculated based on the useful energy. And we will need also these fuel shares into useful energy. Thermal energy uses we will need this for ACM. And here at this level, we will need also to populate our fuel average weighted efficiencies. Again, this is for agriculture, construction, and mining. And here we have this split up by temperature level for manufacturing. So here we need to define our shares of useful energy. This is the structure in terms of temperature range. And then the share of energy forms into thermal energy by temperature level in manufacturing. And the last thing is this average weighted energy efficiencies by temperature level. We saw how we can calculate them. Okay, before I finish this presentation, I just wanted to give you an example, some additional snapshot from MAED user interface to have an idea on the results that you can get, how you can extract them, how you can export them to Excel. So when we finish populating the data in MAED user interface, we save and come here to press calculate. And in this menu, we can check the results. As you can see, we have different category of results. We can visualize them, extract them, and export them to Excel to build some graphs or some. So here we have the results for industry. It includes ACM and manufacturing. We can have separately the useful energy, and we can have also the final demand, or we can come here in the bottom of this to get the total final energy demand. This is an example of the result that come out from MAED model. This is for manufacturing, so we can, if we extract our results and export them, we can build, or you can plot them like this and see the future evolution of energy demand, for example, in manufacturing by energy form, or we can also assess the thermal energy needs in the future. We can see this projection is up to 2035. If we define subsectors, then we will be more able to assess this structure in more details. Here we define basic materials as well as machinery and equipment and non-durables. And we can also, as I said, we can extract the results from the we can have them we can have also the final energy demand by energy form or by sectors. Okay, I will not comment. This is a theoretical case study. Yes. So yeah, and with this I come to the end of this presentation. Thank you very much for your attention, and please, if there is any question or comments, I will be more than happy to answer.
Let me just select something. Okay, so let's just select, for example, this case. Okay, because it's quite an, I would say, an old case. I will just close the door very quickly. Okay, so basically we want to discuss industry sector, yeah? Okay, so so have you seen this software already? I suppose you did, because you did the e-learning process, yeah? So you're familiar, let's say, with the general information, yeah, where you need to define the name of the case, the years of modeling horizon, then you need to define the units. These are usually the default units that would appear. Yes, and then you need to define all your final energies, sectors, and the final energies. So, for example, in agriculture here, in this case, we assume that that specific use of electricity, thermal use, and motive power will be used in the agricultural sector. Yeah, for the construction, as you can see, same is done. So all three final uses will be needed in the construction sector. For the mining, the same, and for the manufacturing, here we have, as Soufiane explained, we have also the distinction between three temperature levels. Yes, so thermal use, temperature high level, temperature medium level, and temperature low level. Yeah, to distinguish different efficiencies of these processes. Okay, so this is our, let's say, structure, defining the structure of our model in the industry sector. Yeah, so these are the ones that were discussed today, and then in the next days we will see how the structure and how is the input data prepared for the service sector, for the household, and for the transport sector. Yeah. Okay, so now we have to go to the energy intensities and the industry sector. Here. So this is where we will insert our input data that we will prepare somewhere else than here, let's say, yeah, because you need to prepare. Usually we do this preparation in the Excel files, and I believe one was shared with you, which will definitely help in this preparation of the input data. So here we will be inserting the energy intensities of motive power, and as you remember, the motive power is treated in terms of final energy. Okay, so here we will calculate these parameters somewhere apart, and this is where we will be putting them. Same as for specific uses of electricity, this is also treated in the final energy terms. Okay, so here we calculated what are the electricity requirements per unit of GDP, per unit of value added in these particular sectors for the specific electricity use. Yeah, and then we will be going to the thermal uses. Thermal uses here is, you remember, here is an additional step where we have to calculate first the useful energy. Yes, so this we will be doing also a part, and the Excel might help you in that. And this is where we'll be calculating the useful needs, thermal energy uses for thermal energy needs for thermal uses in terms of useful energy. Okay, so this is the same structure: agriculture, construction, mining, and manufacturing. Yeah, and for the model to allow it to calculate the final energy, we need to provide the penetrations of energy form. So this is the first thing, and then it will be efficiencies as well, if you remember the way Soufiane was presenting. Yeah, so for each of the let's say sector, to calculate the useful to calculate the final energy demand, the model needs to know what is the energy forms distribution needed in terms of thermal energy. Yes, so this is for agriculture. We can see that, for example, here most of the fossil fuels were used for the thermal energy in terms of useful energy. Yeah, for the construction we can see that there is nothing, and for the mining as well there is no data. And then we need to provide what are the efficiencies of these processes. For example, the fossil fuels, here we can see that the efficiency is at 70%. If you remember, Soufiane explained very well that these efficiencies need to be relative to the electricity, yeah, because the electricity is treated always as a final demand. So even in case our electricity, for example, is less than let's say 100%, so we need to recalculate. We need to adjust these efficiencies of fossil fuels in relative in comparison with reference to the electricity efficiencies. Okay, so here we also have modern biomass and traditional fuels. So this would be our, let's say, final input for the ACM, agriculture, construction, and mining. And for the manufacturing, if you remember, we need to provide different temperature levels, yeah, to basically distinguish between different efficiencies in these processes, yeah, because, for example, in high level we can have a very high efficiency, and then in lower level, in some maybe food industry and so on, the efficiencies of the processes, different processes, thermal processes could be lower. Okay, so for example, this is the share of useful thermal energy demand by temperature level. So as you can see in the manufacturing sector, we have most of the processes that are being done with the high level and medium level temperature, and a small amount is done also with the low level of temperature. And what are the different energy forms providing these levels of temperatures? Here is the next table. So this is also all these inputs, we will have to prepare them separately somewhere. Yeah. So as you can see, for example, in the high level, we have fossil fuels, electricity, and the medium level and low level. For example, solar thermal, you can see, also appears in the low level and medium level, but it's not there at the high level temperature, because you cannot produce the high level temperature with the solar thermal. Yeah. So there is sort of predefined list of these energy forms which can serve these different levels of temperatures, yeah, that are needed. Okay, so all these calculations will have to be done, as I said, apart, yeah. And this is just you will have to input first when you calibrate your base year. In this case, it was 2016. maybe you have a more recent year, and then once the let's say the calibration will be done, then you will have to develop your scenario assumptions. Okay, and the last steps, once you provided the penetration of different energy forms, you will need to provide the efficiencies for these fuels, yeah? So for example, for the fossil fuels, as you can see, these efficiencies are changing. So for example, in manufacturing, fossil fuels in high level, it's 67%, while in low level is 84%. And then if you have also this different iron and feedstock industries, so there where you will have to provide your data. Also cogeneration, it comes here, and it depends what you will when you will model. Then again, you will have to basically input the amount of coke, for example, in this case, used in the pig iron production or steel production. Okay, so this is all these feedstocks which you will, in case you model, you will need to find to prepare the input data for them. But mainly as we said, these are the main inputs, let's say. So these are the efficiencies for the different levels of temperature. These are the penetrations for the different levels of temperature of different energy forms. And this is where we defined our how much of these processes are done in what type of temperatures, yeah? And before that, there were mainly inputs for ACM, agriculture, construction, and mining, and also the thermal use. We define it here also for the manufacturing, which later we split into these different temperature levels. Okay, so this is just a quick, let's say, overview, because it was not somehow intended to go through it. But in case you need more information, then let us know. We will provide you with more details.